Okay, so the plan today is to continue with 7.1, greatest common factor and factoring by grouping, and then start into 7.2, factoring trinomials of the form x squared plus bx plus c. And as I mentioned last time, hopefully you've kind of glanced over the 7.2 material already, so you have a little bit of an idea of what to expect. And then coming up on Tuesday, we'll probably finish up 7.2, I would guess, and we probably won't get through all of it today, and start on 7.3. And again, I'm probably going to say this until you're sick of me hearing it, and then probably say it a couple more times. Yeah, I would strongly recommend pre-reading 7.3 in preparation for Tuesday's class. And again, the idea isn't to come into lecture being an expert at the material. The idea is to skim over the chapter or the section one time, maybe twice, write down a couple of problems if you have questions about things, make sure that they're answered during the lecture, or ask if you still have a question. But we've gotten to factoring, which is kind of the like over the hump uh, material in the course. So if you really drill this well, if you spend the time, if you spend, an hour, 2 hours a day, every day, 5, 6 days a week, working on this material, coming back to it over and over, not doing one big, long session on Sunday evening or something, and you really master this material, the rest of the course will be much easier. And even actually Math 108 will be a lot easier if you master factoring quite well in this course. Um, on the other hand, if you don't, if you just kind of, muddle through it, the rest of the course is going to be challenging, and even say Math 108 will be challenging if you kind of just barely learn factoring just well enough to get by, and and aren't as likely to retain that skill going into the next course. So pre-read 7.3, do some of the 7.2 homework in preparation for Tuesday, and then you'll be ready for 7.3. Okay, the quote of the day today is that the outcome of any serious research can only be to make two questions grow where only one grew before. So if we're making serious inquiries and doing serious research into a non-trivial topic, and kind of like every question that we answer, maybe three more grow out of that almost. So if we ever find ourselves becoming conceited in our knowledge, as Epictetus might say, if we ever find ourselves in that situation, that likely means that we're doing research and not really thinking too deeply about it, because we have one question, we get one answer, and that's end of story. Once we find the answer that we wanted to find, in essence, once we find confirmation of our beliefs, we stop looking, we stop asking questions, and we just walk away. And then it's easy to think that we know everything, but if we really follow that line of inquiry, we're almost certainly going to end up with more questions coming out of that answer than we even originally had. So the more that we know, the more that we understand how much we don't know. And of course, this goes for serious research into a serious topic, not like, uh, what's the price of grapes at the store today or something like that. That's more of a closed-ended question, I think, anyway. And related to this idea, I think, is another plug for philosophy of science. So I mentioned this a little earlier in the course, that our philosophy professor, Drew Van Land, is piloting this course. It's a new course, Philosophy 206, Philosophy of Science. We have the details now. This is up on the catalog, so you can check it out. It's a 3-credit course. There are no prereqs, so you don't need a previous philosophy course or anything else to get into it. You can take it with no prereq. It is on campus at Allegheny campus, Monday and Wednesday, 12 to 1:15, and this is in the fall. And I think this piece of the description kind of highlights what it is. Students will practice using the abstract insights of philosophy to both learn scientific subject matter more effectively and to critically analyze scientific claims. So if you're going into a scientific field, if your plan is to go into, maybe something like nursing or lab tech or something like that, this would be an excellent course, I think, to take. But even if you're not going into a scientific field, we're constantly bombarded with claims of all sorts, many of which are scientific in nature, right? Maybe the first thing we need to ask is, what's the difference between a scientific claim, like, if you eat this food, then this bad thing will happen to you with a higher likelihood, um, versus maybe a non-scientific claim like God exists or God does not exist. So that might be the first thing to sort out, is what kind of claims are even scientific. And then when we make a demand of the individual making the claim that they substantiate that claim in some way, what should that substantiation look like, right? How do we apply ideas of philosophy, ideas of argumentation and systematic thinking and so on to evaluate these claims, to evaluate these folks' support for the claims? Usually we're not looking for support of a scientific type claim to be, well, I have a degree, so listen to what I say, or usually we're not looking for it to be, well, you believed me these 5 other times, so believe me this time. Usually we're asking for something in the sense of empirical evidence, something along those lines. Maybe point me to a peer-reviewed journal article, something along those lines, or maybe point me to a logical argument that from premises that we agree on that reaches this conclusion. So anyway, that's a plug for Drew's course. Like I said, the information is up on the catalog, so keep it in mind if it's something you're interested in. It's a pilot course, so it should be pretty fun to be kind of the first group of students going through this course and experiencing this, and really kind of probably working with Drew a bit to shape what the course looks like in the future. All right, so with all of that said, I want to come back to factoring and the greatest common factor. Now, last time we worked through greatest common factor, and we worked through it very systematically. One thing that we're going to see is that when we're actually factoring, we're going to want to be able to do this a bit more quickly. So for a problem like this, say like completing all 3 of these greatest common factor problems, before I might have given you, say, 6 minutes to complete this, to complete these 3. But we want to be able to do it a lot more efficiently than that. So if you need a little more practice on it, that's perfectly fine. But we want to be able to look at a list like this, 30, 45, and 90, and ask ourselves, for instance, what's the biggest number that divides evenly into all 3 of these? And I might think of numbers like, well, I mean, 2 is not going to work. It works for 30 and 90, but not 45. I can get a little greedier. It looks like 5 will work. Everything ends in a 5 or a 0. Will 10 work? Well, not really. 45 isn't divisible by 10. Well, what's another multiple of 5? Maybe 15. Hey, 15 will work. 30, 45, 90 is 15 times 2, 3, and 6. So it's going to be 15. 15 times 2, 15 times 3, and 15 times 6. And I look at that list of what's left over, the 2, the 3, and the 6, and there's nothing more that I can factor out of there. Right? 2 is prime, 3 is prime, and it's not 2. So 15 is the most that I can factor out. I want to be able to do this more quickly. If I look at 21x squared and 14x, from the number part, I see that 14 is 7 times 2 and 21 is 7 times 3. So I can get a factor of 7 that is common to both of these monomials. And then the most x's that I can kind of pull out of this, that I can consider as factors for everything, is x to the first power. And then similarly with the next one, between the numbers 4 and 6, there's a 2 in common, a factor of 2 in common, but nothing bigger than that. There is one factor of x in common, but not a second. The 6xy to the 5th doesn't have a second x to contribute. And we have 2 factors of y. The y squared limits us. So y squared. We can't pull out, say, a third factor of y, because we could from the y to the 5th, but we don't see that in the y squared. Okay, so let's take about 2 minutes or so and try your best to get through all 3 of these in about 2 minutes. I know that's kind of a tall order when we're just discussing this stuff, for the first time. Was it last class? But try to get through it in about 2 minutes. Try to do it a little bit less systematically and a little bit more intuitively. If you mess up, that's okay. But here we're just seeing what it looks like to go a little more quickly and a little less systematically. So we'll come back in about 2 minutes and discuss the answer. Okay, it's right at 2 minutes. So let's take a look at the answer here for each of these. Again, if you didn't quite make it through all 3 of them, that's okay. But hopefully you made it through at least 1 or 2. So the first one, 24, 36, and 120. We notice a 2 can come out. They're all even numbers. They all have a factor of 2. In fact, they all have a factor of 3 as well, so a factor of 6. We might even realize we can go a little further than that, but let's suppose we recognize the factor of 6, and I see that I could write 24 as 6 times 4, 36 as 6 times 6, and 120 as 6 times 20. So I see that the 6 comes out, but if I'm doing this intuitively, it's not super systematic, so I might have missed something, right? I did pull out a common factor from each of them, but I might not have pulled out the greatest common factor. So actually what I want to do at the end is I always want to look down this list of kind of what I have left over, 4, 6, and 20, and ask, is there any other common factor that can come out of there? And actually, yes, I think since these are each even numbers, 4, 6, and 20, I could actually pull out another 2. So 24 is 6 times 4, but it's also 12 times 2. I could get a common factor of 12, and that's even better. That's even larger. 36 is going to be 12 times 3, and 120 is 12 times 10. Now between 2, 3, and 10, there is no longer any common factor. 2 and 3 are prime numbers that are not the same number, so they don't have any common factors. If we look at 30x to the 4th and 18x squared, we might recognize that something common between 30 and 18 is that they are multiples of 6. 6 times 5 for 30 and 6 times 3 for 18. So I think I can pull out a 6. And then how many x's are common to both? X squared. This would give me 5x squared times 6x squared is 30x to the 4th. And 3 times 6x squared is 18x squared. Nothing common between 5 and 3. Again, they're primes that are not the same number. So this is the best that I can do. This is a common factor, and it's also the greatest common factor. I can't get any more out. And similarly with 9xy to the fourth and 12x cubed y squared. Well, between 9 and 12, I know that 9 is 3 times 3, 12 is 3 times 4. So I think I can pull out a common factor of 3. How many x's? X to the first versus x cubed. There's one x that's common to both. How many y's? Y to the fourth and y squared. There are 2 y's in common for both. And again, 3 times 3 is 9. 3 times 4 is 12. 3 and 4, the kind of leftover bits, share no common factors. 3 is a prime and 4 is 2 times 2. So no common prime factors between the two. 3xy squared is my answer here. Probably took me longer than 2 minutes to explain all of that, but hopefully, you can see that we can do this more intuitively and more quickly than going that super complete systematic approach. That's a good way to kind of start off to get our feet under us, but we eventually want to speed up a little bit. And even if we end up in a situation where we find a common factor, but it's not quite the greatest common factor, we can revise it. We can chain on another step if needed and pull a little bit more off, make a little bit bigger of a factor, and head towards the greatest common factor. Okay, so one interesting thing about factoring, speaking of factoring and kind of the more full chapter 7 context, it really is just basically using the distributive property, but in reverse. So what's the distributive property? Well, that's A times B plus C equals AB plus AC. Usually we're using it this direction. Usually we're distributing A into B plus C. So we're taking the product of two things and making it into two terms. But factoring really is going this way. In other words, I might note that both terms, AB and AC, have a common factor of A. The first term is A times B, and the second term is A times C. That common factor can kind of come out in front of parentheses in front of B plus C. That's just using the distributive property in the opposite direction that we're used to. So I can say find the greatest common factor for some lists of either numbers or monomials. Or I can say something like factor the greatest common factor out from each of the polynomials. What I mean by this is write 5x minus 15 in a way that looks more like this, where I have the greatest common factor times some stuff. So I look at 5x minus 15, and I notice that I have two terms. I have a term 5x and another term 15. And I ask, what's the greatest common factor between these two monomials? My greatest common factor is 5. As a side note, as we're going through here, if you don't see exactly why the greatest common factor is what I say that it is, revert back to that longer, that more systematic process and find the greatest common factor. It's good practice. But here the greatest common factor is 5. 5 goes into 5, obviously. 5 goes into 15. What's left over is a 1 and a 3. No more common factors to come out to contribute. And we don't have enough x's, so to speak, for x to come out as the greatest common factor. We do in the 5x, but not in the 15. So greatest common factor is simply the number 5. So when I look at my greatest common factor of 5, what does that kind of leave over? Or what does that leave behind? 5x equals 5 times what's left over is x. And 15 is 5 times what's left over is 3. So I really see that I could write 5x minus 15 as 5 times x minus 5 times 3. And this looks a lot like the right side of our distributive property up here. Something times x minus something times the same thing. And I can factor that 5 out in front. I can kind of undistribute the 5, that's what we call factoring, to make 5 times parentheses x minus 3. There's nothing more that I could factor out of there. If I tried to factor any x's out, the second term doesn't have any to give up. If I try to factor any more numbers out, like can I make this a 10 times something? The x term doesn't have any more numbers to factor out. So what about this one, 3x squared plus 6x? Well, again, let's come over here, 3x squared and 6x. These are our two monomials that we're going to look for the greatest common factor between. Well, equals. Well, for the number part, I see that both of them have a factor of 3, so I can have a whole factor of 3 there. I can't do any better than that because 3 from the 3x squared was just completely put into our greatest common factor. Here I actually do have enough x's. I have at least one x in each monomial to put some x's into my greatest common factor. I can put x to the first in, not quite x squared because the 6x only has one x to contribute. And then I can rewrite these. 3x squared is 3x times, what do I need to multiply that by to make it 3x squared? Just an x. And 6x is 3x times 2. So again, I can imagine rewriting 3x squared plus 6x as 3x times x plus 3x times 2. And once again, I have this pattern up here, a times b plus a times c, where a is 3x, b is x, and c is 2. I can factor the 3x out in front to get 3x times x plus 2. We could write it that way. There's nothing really wrong with writing it that way, but we'd probably more often get rid of the parentheses around the 3x, but we definitely need to keep the parentheses around the x plus 2. Here's an example where we have a trinomial, a polynomial with 3 terms. So we have 3 monomials to consider. 117x cubed, 39x squared. Note that I'm not really bringing the negative sign over into the in with the monomial to find the greatest common factor. I don't really need that. I can just keep track of that minus sign whenever I do the factoring out, right? The distributive property also applies like this, just as well. So I'm just going to keep track of that minus sign later on. Whoop. Want to get rid of my little arrow here so it's not in the way, but forgot that I had written more stuff up there. 39x squared and 78x. And here was an example where last time we actually did this one, but it was a little more complex to work out. This is one where for the number part, I think I would have to come over here and go through it more systematically. So if you need to do that on occasion, if the numbers are bigger, that's not a problem. So 117, 7 plus 1 plus 1 is 9. So if the sum of the digits is divisible by 9, the whole thing is divisible by 9. So I know that I can break 117 down into 9 times some stuff. Well, 9 times what, maybe 12 is 108. We might know that one. We definitely know that 9 times 10 is 90. 9 times 11 is 99. 9 times 12 is 108. And 9 times 13 is 117. And I might recognize that 39 is 3 times 13. And 78, well, 78, I suppose, is 2 times 39. I know it's an even number, so I can break off a 2. But wait, 39 is 3 times 13, so 78 is going to be 6 times 13. 2 times 3 times 13. So there's a common factor of 13 everywhere. So I might come over here and write my GCF as 13 times some stuff, but actually, let me follow this up. 9, 3, and 6, do they have a common factor? Actually, they do. They have a common factor of 3. So there's still another 3 that I could pop into that common factor, right? I was looking at 13 as possibly my greatest common factor. I know that it's a common factor, but I could actually make it even bigger, get an even bigger common factor out. 13 times 3 is 39, so I write 9 times 3 times 13, or I write 9 as 3 times 3 times 13, or 3 times 39. 3 times 13 is just 1 times 39. And 6 times 13 is, well, that's 2 times 3 times 13, or 2 times 39. So my GCF is 39 for the numerical part. And then how many x's are common between all three? Only one. This 78x to the first is what limits the number of x's I can put into my greatest common factor, just one of them. So I see that I can write 117x cubed as 39x. What number do I need to multiply 39 by to get 117? I see over here that's 3. And then how many powers of x do I need to tack on to turn x to the first and x cubed? I need x squared. Then minus 39x squared is 39x. I don't need to multiply the number by anything, well, just by 1 to get 39. And then x times what is x squared? Just x. And let me erase this to give myself a little more room here. And then lastly, plus 39x times what is 78x? Well, 39 times 2 we see over here is 78. And x times what gives me x? Well, I don't need to tackle on any other x's, so that's all that I need is just that constant 2. We have 3 terms here. Well, if we think about our distributive property, we might remember that our distributive property generalizes pretty nicely. Right, we've seen this before. So A times B plus C plus D is just AB plus AC plus AD, and we can use this in reverse as well if we wanted to. If I have the same A in each of 3 terms, I can factor that A out in front of those 3 terms. So I can certainly factor out this 39x. I could leave it in parentheses if I wanted to. I'll just get rid of the parentheses on this step. Times, and then my first term, what I'm left with is 3x squared. My second term, I have a minus x. And my third term, plus 2. And that's my answer. There's nothing more that I can factor out from that 3x squared minus x plus 2. So that's what I have. Okay, what if I look at something like 3x minus 1? Here I have 2 monomials, 3x and 1. What's their greatest common factor? Well, for the number part, I have 3 versus 1. The only common factor there is just 1. What about x's? The 1 monomial, the constant here, doesn't have any x's, so I can't put any x's into my greatest common factor either. My greatest common factor actually is only 1. I suppose I could write this as like 1 times 3x minus 1, but that's a little silly to do. We have a name for this. If the greatest common factor between the terms in my polynomial is 1, there's nothing substantive I can actually factor out. I could factor out a 1, but that doesn't really do anything interesting. We call this prime. A little bit like how, the number 6 can be written as 2 times 3. That's kind of a substantive difference in the way of denoting it. But the number 2 can only be really written as 2 times 1 if I wanted to get more than one factor. That's really not substantively different. So we call this a prime polynomial because it's a little bit like a prime number. Like it in a sense can't be broken down into simpler polynomials and monomials multiplied together. So this 3x minus 1, that just is what it is. We can't factor anything out of it. We call it prime. And a similar notion to prime numbers, which can't be broken down into their factors, into their composite factors. And then lastly, what if I had something like this? 3 times x plus 3 minus 2x times x plus 3. I might be tempted as kind of a knee-jerk reaction to distribute first, to make this 3x plus 9 minus 2x squared minus 6x, and then go from there. And, most of the time, that's a good thing to do. Most of the time you want to kind of simplify things out. You want to like multiply out, combine like terms, all that good stuff, and then proceed forward. But here, actually, I might notice that each of these terms has a common factor. This is kind of like let me say b times a minus c times a. But if I have b times a minus c times a, that can factor into a times b minus c. Now, a happens to be something complicated looking, parentheses x plus 3, but it can be moved around just like any other factor, just like a factor of x or a factor of 5 or a factor of 7x squared. The factor of x plus 3 can be moved around similarly with the distributive property. It can come out in front. X plus 3, this is just my a coming out. And then what do I have? B minus C. Or B is 3. And then minus C is 2x. Is there anything else that can come out of 3 minus 2x? Is there a common factor between those two terms, 3 and 2x? No, there's not. 3 minus 2x would be prime. And the same can be said for x plus 3. It's also prime. There's nothing that can be factored out of x plus 3. Okay, so that's our answer. Okay, so this is a longer exercise. We have 5 problems here that kind of mirror the ones that we just did. Let me give myself a little more space in between these. Just don't want them to go off the screen. There we go. Okay, that's good. So we have 5 problems here. Take some time to work through these. Maybe take about, maybe actually about 7 minutes or so, maybe 8 minutes, because a couple of these have some bigger numbers to them. Although these are numbers we've seen before in our GCF section, so if you want to just take a peek back a couple pages in your notes, that might give you a little bit of help on a few of these. But yeah, take a look at these. So maybe take about 8 minutes or so. Work through these 5. Work through them carefully and diligently. And also, something I should have mentioned up here is we can check our answer by redistributing. Right? I factored out a 3x from this this polynomial. I can multiply 3x back through with the distributive property, 3x times x plus 3x times 2, 3x squared plus 6x. and that is exactly what I expected to get. So it's good practice to also check your work by distributing back through and making sure that you come back up with the original thing. So take about 8 minutes or so. I don't want this to be a big time crunch, but work through these, diligently. Use the more systematic techniques if you need to, but try to use some intuition when you're able to. And then also if you're, for one or two of these, maybe check your work by redistributing and making sure you get back to the original thing that you started with. So we'll come back in about 8 minutes and touch base on the answers for these 5. Okay, it's just about 8 minutes, so let's take a look at these ones. I kind of ran out of room to keep writing. For the first one, 21x minus 14. We look at 21x and 14 over here. There's a GCF of 7. So we can write the 21x as 7 times 3x, and the 14 is 7 times 2. And we can factor that common factor of 7 out as 7 times 3x minus 2. And that's all we need to do for this first one. The second one, 5x minus 12, the two terms are 5x and 12. And if we look at the numbers 5 and 12, well, even if we go the longer route and look at their prime factorizations, 12 is 2 times 2 times 3. There's no factors of 5 in there. 5 is prime. So there's no numerical factor that comes out other than 1. And the 12 doesn't have any x's to contribute, so we have no x's either. The greatest common factor is simply the number 1. This is a prime polynomial. We can't factor it, or it's kind of as factored as it can get. If we look at 60x squared minus 40x, sorry, these two kind of get jumbled together a little bit here because I was trying to squeeze all the information in. But from the 60x squared minus 40x, from here down to this red line where it says check, that's all this one. So we are looking at the terms 60x squared and 40x, and I see it looks like the common factor as far as the numbers go is going to be 20, because 20 times 2 is 40 and 20 times 3 is 60. And there's nothing more that's common between the 2 and 3. I can't pull out any larger factor than 20. And then if I look at the powers of x, how many powers of x are common to both terms, both 60x squared and 40x? Well, just x to the first. So I can write 60x squared as 20x times 3x. I need to multiply by 3x to make 60x squared. And I can write 40x as 20x times 2. And that gives me a common factor of 20x that I can factor out into 20x times 3x minus 2. And maybe here I want to check this. I do 20x times 3x minus 20x times 2, or that gives me 60x squared minus 40x. And I notice that that's exactly what I started with up here. So I've checked that, that this factorization is correct. In this 3x minus 2, there's nothing more that I can factor out, so I am done with this one. If I look at this example, I have yeah, so that's what I'm getting to now, is I kind of did this in a little bit of a funky way, just to show you how in practice you might end up going about this. 66, 18, and 36 are kind of big numbers. I could come off to the side, systematically go through, get each of the prime factorizations, do that whole method. But maybe I took a guess here. Maybe I said, okay, there is a common factor of 2x to the fourth. We know that there's 4 factors of x in each term. Those are usually the easy ones to find, is the variable powers. Kind of ironically, the variables are easier to work with than the numbers in this case. I know that x to the fourth is a common factor. I also look between 66, 18, and 36, and I recognize that they all have a factor of 2. So let me try 2x to the fourth. I know that it is a common factor. Is it the greatest common factor? Well, we'll see in a minute here. So I have 2x to the fourth. What do I have to multiply that by to get 66x to the fourth? I have to multiply that by 33. 2x to the fourth has to multiply by 9x to get 18x to the fifth, and by 18x squared to get 36x to the sixth. So let me factor that 2x to the fourth out, and I get 2x to the fourth times 33 plus 9x plus 18x squared. And here I actually, I want to get into this practice. This is a good practice to get into for the rest of chapter 7 and really any time we're doing factoring. I want to take another look. I want to say, okay, can I factor anything else out? I still have this bit here, this 33 plus 9x plus 18x squared. is there anything else you can factor out of here? Well, no more x's because the 33 term doesn't have any x's to contribute. But I actually do notice that between the numbers 33, 9, and 18, these are smaller numbers. Now I can more easily recognize, oh, wait, there's actually a factor of 3 in each of those numbers. There's still another common factor of 3. I can actually go ahead and pull this 3 out as well. Now, if you recognized immediately, way back up here, that there was a numerical part of the common factor of 6, great. If you use 6x to the fourth here, that's even better. If you can do it all at the first step, that's great. But my point here is that even if you miss that, even if you just kind of take the obvious kind of chip off of the block and make some headway, that'll make the number smaller. And then as long as you're diligent about always going back and carefully investigating if there's anything more that you can take out, even if you don't get the GCF right away, it's more easy for me now to see that, okay, there's a factor of 3 remaining. I can factor a 3 out, put that onto the 2x to the fourth, making 6x to the fourth. 33 is 3 times 11, so the 11 is what's left over. 9x is 3 times 3x, so 3x is left over. 18x squared is 3 times 6x squared, so 6x squared is left over. And now I probably want to check my work. So if I distribute, I get 6x to the fourth times 11 is 66x to the fourth, plus 6x to the fourth times 3x is 18x to the fifth. And, well, wait, if I multiply these ones, I get plus 36x to the sixth. But wait, I wanted a minus 36x to the sixth. Oh, I made an error here. I see that this isn't the same. Where did I make a mistake? Oh, when I have this minus, I copied it as a plus. So this has to be a minus. This has to be a minus. Let me go ahead and fix that. So if you caught that, great. I was hoping that you all were kind of paying attention and hopefully were wondering where that minus turned into a plus. Nobody called it out in the chat, but if you caught that, great. But that is the reason that we check at the end, because it is really easy to make little mistakes, either with like factoring our numbers and just making a silly arithmetic error, or copying negatives, things like that. Really easy to make little mistakes like that. So factoring at the end, or sorry, distributing at the end to check our factoring. This is now a minus, and now we can check it off and we can confirm that our solution is correct. So especially whenever we're doing a lot of operations like this one, when we have a simpler problem like this one, maybe it's not so error prone, but when we're doing something like this one down here, we definitely want to check at the end. We definitely want to distribute, double check that everything matches exactly as it should. And if not, we don't just want to like randomly change something so that our answer matches what we think that it should. We want to go back and find the source of the error. What was the mistake we made? And then track it through to fix things. As a little side note, there's a fairly famous YouTube professor. He's actually a professor at a college, unfortunately. And I was watching one of his Calc 3 videos that one of my students asked me about. And basically, he went through an entire problem. From first principles, he goes through the whole problem. He gets an answer. And this was his pedagogical point. This was his teaching point. This wasn't just like him slipping up and saying something silly when he didn't mean to say it that way. His whole point was, we got this answer. We know that this answer is wrong. We suspect it's wrong. He actually was incorrect in his logic on why it was wrong. He thought that there was more symmetry in the problem than there actually was. But he says, we got this answer. This answer we suspect is wrong, even if we know it's wrong, whatever. He says, well, since we know that this answer is wrong and we should have a bunch of stuff cancel out because of the symmetry, which again, he was applying the symmetry incorrectly there. Well, we're going to go back in the problem and change this plus to a minus and then track that through. He didn't say, we're going to go back in the problem and, oh, okay, this plus should be a minus because we made this error and this is the reason it should be that way. It says, no, we're going to change this plus to a minus so that it makes everything turn out to be 0, which is the answer that I wanted. That is not how you do math, right? There needs to be a systematic approach. So if I see an error at the end, and by the way, I emailed him on YouTube. I was like, hey, buddy, I think, yeah, you got a mistake here. Here's where the symmetry is broken. The symmetry, it's like a magnetic field kind of problem, and the thing moving through the magnetic field was symmetric, but the field itself was not symmetric. So you need the symmetry in both of them for everything to kind of cancel out properly. But I even brought this to his attention, and he kind of like minorly acknowledged. He's like, "Oh, thanks for letting me know. I'll check it or something." The video is still up there, so don't trust what folks on YouTube say, even if they have good credentials. And for that matter, don't trust what I say, right? I mean, if we're going through a problem and you say, "Hey, that doesn't look right," I think you dropped a negative there or something. I make mistakes from time to time as well. I mean, hopefully I don't make too many mistakes, and hopefully I most of the time catch them when I do make a mistake. But I threw this one in there, number one, to see if you were paying attention. Hopefully you were. And number two, to show you that if we get to the end and we do our check and something doesn't go right, how do you approach that? You don't just work from the bottom up and try to fix your answer to make it, look good. You go back through your logic and you say, where did I make a logical error? Until you can find the logical error that you made, don't correct your answer. Find the logical error you made and then track it through the problem. Or if it's too complicated to do that, erase and start over from the point where it was good and then work from there. So, that diligence and that thought process of we don't do something unless we can justify it is one of the central tenets of thought in math. And it's, maybe unfortunately sometimes less common than one would hope that it is. Okay, and then I kind of ran out of space, so we will do this one from start to finish. So here we have actually, what looks like the hardest problem, but is actually one of the easier problems in the list. We have something times something else plus something times something else. And this 2x minus 7 is common to both of these terms. Again, I could try to multiply everything out, get a bunch of different terms, combine like terms, but that's going to be really challenging to factor. I already kind of have some of the work done for me. I already have, b times a plus c times a. I might as well leverage what I have here and just move forward from this point. I can just factor out a 2x minus 7 that is common to both terms. That leaves me with 4 plus 5x. And now I do want to diligently go through and check in 2x minus 7 between these two terms, 2x and 7, is there any other factor that can come out? Numerically, 2 and 7, both prime numbers, not the same number, no common factors between them. And the 7 term does not have any x's, so no x's can come out. Do the same thing over here. Between 4 and 5x, between those two terms, 4 is 2 times 2, 5 is just 5, no common factors between the two, and the 4 doesn't have any x's, no common factors can come out of here either. This is the best we can do. Okay. Any questions so far? Okay, now let's take a look at factoring by grouping. The idea of factoring by grouping is to end up with something that looks like this, and then we can apply basically this step to get a fully factored form. Okay, so let's take a look at this one. We have m times n plus 4n plus 6m plus 24. We have actually 4 terms here. We also might notice, probably just by looking at it, that there is no common factor that can be factored out of all 4 terms. The mn, the first term, has only the number 1, in front of it, basically. So there's no numerical factor that can come out. There's not like a factor of 2 or something that's common to all of these. And we see that our variables are m and n. And the 24 at the end here has no variables on it. It has no m's, no n's. No m or n can factor out of all 4. We might be tempted to write that this is prime, but there are other ways to factor things. One thing that could happen is a common factor comes out, just basically a monomial comes out and leaves behind a binomial. But another way that things could factor is like this one here, where we end up with a binomial times a binomial. Sometimes we can leverage the ideas of greatest common factors to factor these binomial times binomial situations. How might that work? Well, what I'm actually going to do is I'm going to choose to split this problem into 2 subproblems. Now, I want to stress that sometimes this works and sometimes it doesn't. Of course, the ones in this section most of the time are going to work because we're demonstrating it in this section, but this doesn't always work. So mn plus 4n, if I look at just those two, if I look at just mn plus 4n, are there any common factors here? Yeah, actually, there's a factor of n that can come out. So I can write, let me actually use 2 different colors for these to keep straight what's what. I'll make the first one green and the second 2 blue. So mn plus 4n, I could choose to write that, those 2 green terms, as n times m plus 4. Then for the blue one, 6m plus 24, I see pretty readily, I think, that there's a factor of 6 here. 6 times m plus 4. And hey, I actually realized that this looks a lot like this problem up here. I have a common factor of m plus 4 in the green term and in the blue term. This green stuff is all one term now, connected by this plus to the blue stuff that is all a second term. They each have a common factor of m plus 4. I can factor that m plus 4 out, leaving me with n plus 6. So if I multiply m plus 4 times n plus 6, I should get this thing up here, these 4 terms. One kind of clue that factoring by grouping might be something to look at is if I have 4 terms. Because when I have 4 terms, I can split them into, say, a first 2 and a second 2, and try to do something like this. Try to factor the first 2 and the second 2 separately, and then end up with a common factor that can come out of what remains. Okay, so let's look at the next one. Somewhat ironically or strangely, it can sometimes actually be easier to do some of these factoring processes when we have more than one variable, because it's just clearer what is going in what place, right? When I have a lot of numbers, when numbers get multiplied together, like when I have 6 times 4, it becomes 24 and kind of obscures the fact that that came from 6 times 4 and not 8 times 3 or 12 times 2. But when I have m times n, that just always looks like m times n. It never kind of combines to make a p or something that looks completely different. So sometimes whenever I have 2 variables, it can actually be a little easier to see what's going on. And when I have 1 variable, it can be a little more complicated. Now here I've written this in a very suspicious way. m squared plus 6m minus 12m minus 72. You might say this is a little silly. Why don't we combine our like terms first? Make this m squared minus 6m minus 72. Right, so we could do that. This would have fewer terms, but it would actually be harder to factor. Actually, I kind of like factoring by grouping. This isn't too difficult to do, especially relative to some of the other factoring methods. If I can take this and kind of uncombine the middle term, if I can break the middle term into the sum of two like terms, and in particular, if I can do that in just the right way, it only works if we do it in a specific way. If I split this minus 6m into like, whatever, minus 100m and plus 94m, it's not going to work. But if I do it just this way, split it into plus 6m and minus 12m, what happens? Let's try the same thing. Maybe I'll keep my color scheme the same. I'll look at the first two terms and the second two terms separately. I'm going to look at m squared plus 6m. And really all I can factor out of here is an m, and I'm left with an m plus 6. And for the blue, negative 12m, I do want to keep my minuses attached now. Minus 12m minus 72. I can factor, well, 12 times 6 gives me 72, so I can factor a negative 12 out, and I'm left with m plus 6. Be careful with that minus there. It's not an m minus 6. The minus 12 distributes to the plus 6 to make a minus 72. So I have m times m plus 6, and then plus a negative 12 times m plus 6. And once again, I have this common factor of m plus 6. Give me 1 second here. Sorry, I didn't want to sneeze in your ear and blow your eardrums out. Um, so I do have this common factor of m plus 6 in both the green term and the blue term, and it can now factor out. I can factor out m plus 6, and what's left over is m plus a negative 12 or m minus 12. And again, I go through and I check each of my factors, m plus 6 and m minus 12, to make sure each of them are prime. And they are. There's nothing more that can factor out of m plus 6 or m minus 12, so this is my answer. Okay, and then if I look at this third example, x squared minus 3x plus 2x minus 8, I'm going to take the same approach. And over here I have x squared minus 3x is x times x minus 3. 2x minus 8. Well, a factor of 2 can come out of here. 2 times x minus 4. And here, what it would have been really nice to end up with is the same thing here and here. But I actually get two slightly different things, x minus 3 versus x minus 4. And I really can't proceed. I'm going to just put a frowny face here. I really can't proceed from here. Now, that doesn't mean that this polynomial cannot be factored. It doesn't even mean that it can't be factored by grouping, but it just means that this particular approach didn't work, right? So this would be a little bit like if I broke this minus 6m up some other way other than plus 6m and minus 12m, then this wouldn't have worked out as nicely. I wouldn't have gotten the same thing here and here. And that's kind of what happened down here. So this might still be able to be factored, but I might have to use a more advanced technique, or I might have to kind of reconsider how I broke up what amounts to negative x here. Minus 3x plus 2x was not the right choice, perhaps. So it might still factor, it might not factor, but at the very least, we're not able to proceed directly from this point and factor by grouping. So, you know, basically we just run into a roadblock here and we have to back up and do something else. You know, that something else might look like something from section 7.2. Okay. Cool. Okay, so work on these two exercises. Maybe take about um, 4 minutes. I think 4 minutes is probably enough. So 4 minutes for these two, and then we'll come back and discuss the answers. Okay, it's just about 4 minutes, so let's touch base. So for our first one, we can think of the PQ minus 10P as kind of uh, the first kind of grouping that we're gonna pull off, and then the 8Q minus 80 as the second. PQ minus 10P has a common factor of P that can factor out, leaving a Q minus 10. And 8Q minus 80 has a factor of 8 that can factor out, leaving a Q minus 10. And if you were watching me write out uh, my work, I mistakenly made this PQ plus 10P at first and then realized that I had a copying error. So I think I jinxed myself by intentionally putting in that mess up earlier, and then I got an actual sign error. But we got P times Q minus 10 plus 8 times Q minus 10. And now we have this common factor of Q minus 10 in each of the blue term and the green term. It can factor out in front, leaving me with P from the blue term and then plus 8 from the green term. So that's where the P plus 8 comes from, factoring out the Q minus 10. And again, I always want to come back and just double check. Q minus 10, that's prime. There's nothing else that can factor out of that. If it was like 2Q minus 10 that I ended up with, I could factor that into 2 times Q minus 5 times P plus 8, but nothing like that here. And P plus 8 also prime, nothing more that can factor out of P plus 8. And then my second one, x squared plus 5x minus 3x minus 15. And again, I take my first two terms, the x squared plus 5x, a factor of x can come out of there. And my last two terms, negative 3x minus 15, a negative 3 can come out of there, leaving me with just factors of x plus 5. And then the factor of x plus 5 can come out in front, x plus 5 times x minus 3. And as always, I do one last check. X plus 5 is prime, x minus 3 is prime. Nothing can factor out of either of those two. No greatest common factors can come out. So that's my final answer. Any questions on 7.1? Okay. So now we're moving into 7.2, factoring trinomials of the form x squared plus bx plus c. So this is where grouping is not going to work, at least it's not going to immediately work. Maybe we could, maybe one strategy will be to set ourselves up to use grouping. That could be a possibility, but at least just looking at it on the face of it, we only have 3 terms. We can't split them into a first group of 2 and a second group of 2 to try to group and then group again. So what would our strategy here look like? We also notice that we're not going to be able to factor any common factors out of here. The x squared term has just a numerical coefficient of 1. That's not going to mesh with b or c to be able to factor any greatest common factor out. And the c term doesn't have any x's in it, so no x's can come out. So no numbers can come out, no x's can come out. The greatest common factor of these is going to be 1. So we don't get anything from the greatest common factor. We don't get anything from factoring by grouping. What's our approach here? Well, we do notice these examples up here kind of came from, say, x squared plus 2x minus 15. Right, and then we broke the 2x into 5x minus 3x. Or this one really came from x squared minus x minus 8. I mean, it didn't, we kind of, didn't quite work here, but that's what it came from. This one came from m squared. Oh, well, I already actually wrote it. M squared minus 6m minus 72. These examples up here, the ones with one variable and not two, actually came from this kind of a setup. And what did the answers look like? It looked like binomial times binomial, or binomial times binomial. Let's try to come up with a general strategy to rewrite x squared plus bx plus c as x plus m times x plus n to factor into the product of two binomials. Now let's think about this a little bit. If I want to write this as x plus m times x plus n, let me actually multiply out x plus m times x plus n. Well, my first give me x squared. My outers give me plus nx, my inners plus mx. So that's plus m plus nx. And then my last give me plus m times n. So that's what x plus m times x plus n is for whatever m and n I choose. But I want to make this the same as x squared plus bx plus c. So I'm going to set this to x squared plus bx plus c. So basically, my problem boils down to this. Maybe I'll write it in red. It boils down to, given b and c, so if a problem is presented to me, factor x squared plus 2x plus 4, something like that. Find m and n. So typically b and c are given in the problem statement, and it's my job to find m and n, which are the ways this factors. And implicitly here, given b and c that are integers, find m and n that are integers. We can kind of generalize the idea of factoring into factoring over different numerical systems, but for our purposes, when we're talking about factoring, we're essentially always talking about factoring over the integers, as we would say. So b and c are integers, and we're looking to factor that into x plus m times x plus n, where m and n are integers. Integers are whole numbers or negative whole numbers. So these could be positive or negative, but they're not going to be decimals or fractions. So this is what our problem boils down to. And what does our solution look like? Well, I need to find an m and n such that two things are true. One, that their sum is b, and two, that their product is c. I'm looking for two numbers that multiply to give me c and then add to give me b. Okay, let's go through the process of multiplying out one of these binomials just with numbers so that we see it maybe a little more clearly. X plus 1 times x plus 2 by first give me x squared, and then plus 2x plus 1x plus 1 times 2. Or that's x squared plus 2 plus 1x plus, and then maybe I'll write it as 2 times 1. Or that's x squared plus 3x plus 2. So if I were to say factor x squared plus 3x plus 2, the answer that I'm looking for is x plus 1 times x plus 2. Since factoring is using the distributive property in reverse, we might think of this as an inverse problem. The kind of forward problem would be the way that we did it here. This is the forward direction. And factoring is our inverse direction. It's kind of going back up this line of reasoning in some sense. It tends to be the case that inverse problems are more challenging than forward problems. We usually call the forward problems because they're direct applications of certain principles or properties, something like that, like the distributive property. And the inverse problem is kind of saying, you know, where did I need to start to end up here by applying, say, the distributive property? or it's kind of, in a sense, applying the distributive property in reverse. There's not technically a forwards or backwards direction for the distributive property, but there's a way that we use it more often and a way that we use it less often. Okay. So we're going to go through several examples here. And I think this is one of those topics that it really just helps to go through a lot of examples. So we'll go through a couple examples. We'll do a couple exercises, a couple more examples, a couple more exercises. This looks like a lot of exercises, but we'll see that this 100 being the same at the end here actually makes the 4 of these almost like just one bigger exercise. So we're going to go back and forth a couple of times. I'll do a couple examples. I'll let you do a couple exercises and so on. We have 14 minutes left. We might get through like one example and one exercise or something like that, and then leave the rest for next time. Okay, so I have x squared plus 8x plus 15. Remember, we start with x squared plus bx plus c, that's given. And our goal is to find m and n such that this is x plus m times x plus n. And what was my strategy to do this? What are the criteria for my m and n? I know that m times n has to be c, and m plus n has to be b. And I typically start with the product first. So I start by looking for m times n equals 15, but I also need that m plus n equals 8. Now I can just think through some examples and kind of basically brute force it, just guess and check here. I don't want to do that. I want to start doing this systematically. This is an easier problem, so it's going to be easier to just kind of, whack it with a sledgehammer, so to speak, and figure it out. But if you don't develop the strategic approach on the easier problems, it's much harder to start developing it on the harder problems. So we're going to take our time and go through the strategic approach here, and that might not be necessary for a problem like this. You might see right away that m and n are 5 and 3, but we're going to do it the careful way, so that when we get to harder problems where you don't see the answer right away, then you've built up that framework. So we're going to start off looking for combinations, for pairs of m and n, where m times n equals 15. And for the time being, we're only going to consider positive m's and n's. These have all been set up so that the positive ones will work. So the smallest that m can be is 1. And if m is 1, then n has to be 15, and that works. 1 times 15 is 15. M could be 2, but 2 is not a factor of 15. 2 times what gives me 15? I can't multiply by an integer. I have 3 times 5, that works. 4, well, 4 times something is 15, not an integer solution. And then if I come down here to 5, well, now I'm just starting to repeat myself. I already do that enough already in my lectures. We don't need to keep going. We already have 5 accounted for, because multiplication is commutative. M times n is the same as n times m. I don't need to rewrite 5 times 3. I've already got that here. So 4, and then the next one will be 5, but I've already got 5 accounted for, so I can stop here. Now, of these, let me say, what is m plus n? 1 plus 15 is 16. 5 plus 3 is 8. So this list, the black list here, already satisfies the product, the m times n equals 15. We've already got this satisfied by construction. Everything in this list of m and n black numbers, 1 and 15, or 3 and 5, satisfies m times n equals 15. The question is, which one of these also satisfies m plus n equals 8? And that is this one. M equals 3, n equals 5. Or n equals 3, m equals 5. Everything's commutative. It doesn't matter too much which way you have it written. So I see that x squared plus 8x plus 15 is x plus 3 times x plus 5. And I can check this. I can FOIL it out. My first give me x squared plus 5x plus 3x is plus 8x. And my last give me plus 15. And that looks good. So x plus 3 times x plus 5 is my answer. Again, could you have, just from this point, saved yourself writing all this out and gotten to the answer? Probably. But we want to know how to do this process over here for when the numbers become larger and more challenging to work with, and we can't see the answer so readily. We want to practice this strategic approach on the simpler problems, so when we come up against harder problems, we know how the strategic approach works if we have to fall back on it. Okay, let's do one exercise here. This one's going to be pretty straightforward, but try to do this one. X squared plus 8x plus 7. And, oh, didn't want to go that far. Let me move this up a little bit so that I can have this one on the screen, but work on this exercise, x squared plus 8x plus 7, using this same approach. And it's actually going to be, there's not going to be a whole lot to do, but maybe take about 2 minutes or so and work through this, and then we'll come together and work through it together for the last few minutes of class. So in about 2 minutes, we will touch base. Okay, it's just about 2 minutes. So if we look at this one, x squared plus 8x plus 7, we're looking for two numbers, m and n. In this case, positive integers. We'll relax that and allow negatives in a little bit here. But for now, positive integers. We're looking for two positive integers whose product is 7 and whose sum is 8. We start by chipping away at the product. M times n equals 7. And we list out, starting with 1 times 7, of course, is always going to be a possibility. So if m is 1, n would be 7. Can m be 2, 3, 4, 5, 6? No, because there's no other integer, positive integer, that can multiply by to get 7, and 7 is prime. So I've listed all of the m and n combinations, positive integers. They can multiply to give me 7. In this case, there was only one of them. In the previous case, there were two of them. But in more complicated problems, there will be more than just a couple of them. And then I come over here and I say, okay, well, now let me go down for each possibility that I've identified, each of these rows. What is m plus n? I'm looking for the row where m plus n is 8. And of course, 1 plus 7 gives me 8. That was my only one to choose from, so that made it pretty easy to find. So m equals 1, n equals 7 does the job. And then I can say that x squared plus 8x plus 7 equals x plus 1 times x plus 7. And of course, multiplication is commutative. If you wrote x plus 7 times x plus 1, that's perfectly fine as well. And then lastly, to check our work, let's FOIL this out. The first give me x squared. The outside's plus 7x, the inside's plus 1x, so plus 8x. And the last 1 times 7 is 7. And that's exactly what I started with, so I'm confident in this solution. Okay, so that's where we're going to stop for today. When we come back, we'll again kind of keep drilling this. We'll look at, some things like, 21, which factors in a couple different ways, or 18, which factors several different ways, or even numbers like 60, which factor a whole bunch of different ways. So when we come back, we're going to look at more challenging problems. So that's why it's important to understand the systematic approach. The guess and check approach is great once you kind of get your feet under you and understand the method and want to do things a little more quickly. If you can guess and check and knock out the answer quickly, great. But we want to understand the systematic approach as well for when we need it. So for Tuesday's class, take a look through section 7.2, try to work through a couple of problems, try to do this systematic approach on all the problems. Again, at this point, we're practicing the systematic approach. So even if you could just kind of guess what the answer is and end up getting it right, do the systematic approach to get your feet under you with it for when it's needed. So look through 7.2 in preparation for Tuesday's class, and then also pre-read a little bit of 7.3 as well. Take a look through there and see how I think I have some of 7.3 down here. Oh, no, I didn't put it at the end of my notes. But when we have ax squared plus bx plus c, where a is not 1, how does that change things? If I have, 3x squared plus 2x plus 5, how does the treatment of that change from if I have x squared plus 2x plus 5? And it's going to feel a lot different, but it's also going to kind of use this factoring by grouping idea, this method. So take a look through 7.2, 7.3 in preparation for Tuesday, and that will set you up well for understanding this really foundational idea of factoring in the first couple of sections of factoring. All right, let me stop the recording.